Hey Math 7, I wanted to do this worksheet here with you. I know we ran out of time as we were doing it in class yesterday, so I wanted to go ahead and finish it with you, and then you can be able to put it into your quarter 3 section of your notes, and it would be complete and accurate for notes. Alright, so I wanted to take a look back at the one that we did get to do. I added a few pieces of information that kind of help us with this process for your notes. But as we're reading, you're going to be looking for, just like you would any word problem, looking for the key words that stand out. Alright, so for this one, we see keyword or value of 4 dogs. And then we see that they talk about that they adopt more dogs, but they didn't give us a specific number of dogs that they did adopt. So that's kind of an unknown. So I gave it the variable x. Find the table, equation, and graph that shows the relationship between the number of adopted dogs and the total number of dogs in Fred's family. All right, so I wanted to go ahead and identify or determine the variables and what they mean. So I wrote myself some notes. That x, or my input, is going to be the number of adopted dogs that they bring in at a time. Maybe they're a foster family for the Humane Society, and they might have a number of adopted dogs or foster dogs changing periodically through time, but then they always have their own personal 4 dogs that stay. So that's kind of how I'm interpreting this word problem. All right, and then Y would stand for the total number of dogs in the house, and I got that from the question that they're actually asking in this word problem. So you can find out the total number of dogs in Fred's family. All right, so your answer for this one would be number of total dogs. So the equation that we glued in would be the number of adopted dogs plus their 4 dogs will tell you how many dogs are in the house at a time. All right, so that's this equation. And then if you looked and saw that, yes, if I had 1 adopted dog in the house plus the 4 original dogs that always stay, you would have a total of 5 dogs in the house. If you had 2 adopted dogs, you would have 6 in the house, 3, 7, 4, 8. So this table does match up with this equation. And then the graph that you would put in there would be this one. Now, if you're looking at this equation, you would expect to see a dot right on the 4 for the y-intercept, your starting point of 4 dogs in the home at all times. And then you can see this is an additive relationship, so we would rise 1, run 1, rise 1, run 1. And if you checked these points, they are the ordered pairs over here. So at 1 adopted dog, you would have 5 in the house. At 2, there would be 6. At 3, there would be 7. And so forth. So this is the correct graph for this set of data points. Okay, so we're going to look into the second one. Now, we had begun this one and ran out of time, and I rushed too quickly. So if you had glued down the ones that I had originally thought, we need to read this a little bit more carefully and look at our cue words or our clue words. All right, so every state has 2 senators. The number of electoral votes that a state has is equal to the total number of U.S. senators and U.S. representatives. Find the table, equation, and graph that show the relationship between the number of representatives and the number of electoral votes. So if we're going to write this information in, we're going to have an X, the input, and a Y, what our answer would be or what we're specifically looking for. And I did underline what this word problem is looking for. So we're looking for the number of the number of electoral votes. That's our final part here. Okay, so the number of votes that each state gets when you look at the relationship between the number of representatives. Okay? What we do know is that each state gets 2 senators. What we don't know is how many representatives they get. Okay? So we have a constant that is the same between every single state, and that's 2 senators. The thing that changes is the number of representatives. So that's going to be our input, number of representatives. And we have a starting point. Every state, or an additional point, something that has every single state has the same of, and it's where we start our number of votes. So if a state, this would not happen, but if a state had no representatives, they would still have 2 senators and get 2 votes. So What equation can we use to represent that? Well, that would be an additive relationship. We are adding two senators. We have a starting point or an additional amount. So our equation would be this one right here, y equals x plus 2. So we would have the number of votes would equal the number of representative, that changes by state, plus their two senators' votes. Okay, so then we've got to look for the table that coincides with that. So it would be, let's say that we had one representative plus the two senator votes would give us 3. So we need one that has an input of 1 and an output of 3. And we have, I know, 2 of them like that. So we need to decide which one shows our additive relationship of plus 2. Where does the pattern show plus 2? So this one is plus 2 or times 3. This one, if I did plus 2, should give me 4. So this one is not an additive relationship. So let's check this one. This one, if we do plus 2, we get 3, plus 2, 4, plus 2, 5, plus 2, 6. So this is the correct table. So this one is going to go here. And then we got to find the appropriate graph that goes with it. So we're looking for, I'm going to put my table off to the side here, what we're looking for. The graph that has points 1, 3, 2, 4, 3, 5, and 4, 6. And that would be, it's not this one because that's 1, 2. This one's 1, 3. So let's check and see. 2, 4, 3, 5, and 4, 6. So we have found our graph. And so you're going to want to make sure that these 3 are glued in for this problem. All right, this next one says Jolene is packing her lunch for school. The empty lunchbox weighs 5 ounces. So by itself, the lunchbox weighs 5 ounces with nothing in it. Find the table, equation, and graph that show the relationship between the weight of the items in Jolene's lunch and the total weight of the packed lunch. All right, so this is what we're looking for, the total weight of the packed lunch. So we know automatically that that's going to be our y, our answer, okay, or our output. So the y stands for total weight, and the x stands for, we're looking for the relationship between the weight of the items in the lunchbox and the total. So it would be, if I put just an apple in my lunchbox, it's going to weigh very differently than if I put a sandwich and a cup of yogurt and an apple. All right, so the X stands for the weight of the items in the lunchbox, okay, or what we put in the lunchbox. All right, so we need to look for an equation that if we change the input of how much the items weigh in our lunchbox, we got to have an additional or a starting weight, which we read in our word problem was 5 ounces. So we have our input of how much the items inside weigh plus our 5 ounces plus the additional 5 ounces. So that's another additive relationship of the weight of the items in the lunchbox, X, plus the 5 ounces that the lunchbox weighed to begin with, would give us the total weight of the lunch once it's packed, depending on what we put in it. So then you look for the table that coincides with that. So if we only have 1 ounce of something in our lunchbox, maybe a marshmallow or 2, plus the 5 ounces of the lunchbox itself, we would have a total weight of 6 ounces. So you find the table that has the 1, 6. All right. And then we would just double check and make sure that this shows an additive relationship. 2 ounces plus the 5 ounces gives us 7. 3 ounces plus the 5 ounces gives us 8, and 4 plus the 5 gives us 9. So that is the correct table for this equation. And then find the graph that coincides with it. So we're going to look back at our remaining graphs here. And we're going to look for one that has the points 1, 6, 2, 7, 3, 8, and 4 9. So 1/6, that is not it. That is not it either. That is not it. And that one is it. And we see that it just goes up 1/1 every single time. So this is the proper graph for that one. Okay, so if you notice, the whole front side of your worksheet, they are all additive relationships. Okay, they all would have a y-intercept and just rise and run 1 on our graph. And if you were checking the tables, the pattern jumping from x to y on all of them would be a pattern that shows addition. Okay, so these are all 3 additive relationships, and you can see in the wording how they talk about adding something to an original amount in order to come up with your final answer. All right, so flip your page over and we're going to look at the back. All right, so the next one on the front, or the top of the back side, talks about Franny ordering 3 DVDs per month. So I see a keyword right there that needs to stand out every time you're reading worksheets like this, okay, from her DVD club. Find the table equation and graph that shows the relationship between the number of months and the total number of DVDs that Franny has. So we see total number of DVDs is going to be our answer, right? Total number of DVDs. And then what's changing every single time, the input that is changing every time, is the number of months. Because we know how many she gets per month is 3. So that's our rate. The rate of 3 every month, every 1 month. Okay, so our x is number of months. So if we get 3 for the first month, we're going to have a total of 3 DVDs. Okay, if we have 3 for 2 months, we're going to have a total of 6 DVDs. Okay, so that is showing that relationship of the per month. If we don't join the DVD month club and we don't have any months that we're calculating, of course we would have no DVDs, so it would be a 0, 0, a true proportional or multiplicative relationship. So we need to find something where we are multiplying 3 to every month. So the equation would be y equals 3x. So for every month we would multiply by those 3 DVDs we get per month, that keyword per. All right, so then we look between our tables and we see that this is the one that represents a pattern of times 3. So 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9, and 4 times 3 is 12. And then you take your remaining graphs and you find which one we would use. Okay, let me get them up here. So we're looking for the point on 1, 3. Well, there's 1, 2. There's 1, 4. There's 1, 3. Very good. And then 2, 6, 4, 12 are what are graphed there. Okay, so this would be your proper graph for that equation. Okay, the next problem. Ollie sells bracelets for $2 each and donates the money he collects to a charity. So we already see some keywords here. $2 each. Find the table graph equation that show the relationship between the number of bracelets sold and the total donation that he will make. All right, so our X, our input, would be number of bracelets, because that is what will change off and on. Bracelets, there we go. And Y would be the total donation. Okay, and then the piece of information that we need right here is the $2. $2 each suggests that for every bracelet we're charging $2, and that is a keyword for multiplication, so we need to find something that is times 2. So our equation that we have left is the one you peeled off of the front probably. Right here, y equals 2x. And then the table that represents that would be 1, 2, 2, 4, 3, 6, 4, 8. And then you would find the graph that represents 1, 2, 2, 4, 3, 6, and 4, 8, which is this graph right here. All right, and then the last one, Frank's karate class meets 4 days every week. There's another keyword. We have 4 days and we have every week. So those are our keywords. We're going to find the relationship between the number of weeks, that's going to be changing, and the total number of karate classes. All right, so our number of weeks will be our input or our independent variable, and our y will be our output or our answer, and it's the total number of classes. Okay, and then the piece of information we need is that it's going to be 4 every week. So 4 times the week, which we don't know, so it would be 4 times x. So our equation is y equals 4 times x. And then our last table shows that as 1, 4, 2, 8, 3, 12, 4, 16. And our graph shows 2 of those points, 1, 4, and 2, 8. All right. I hope that helped you guys take the verbal descriptions, the word problems, the practical application for using linear equations, and helps it make a little bit more sense to you. Go ahead and add this into the quarter 3 section of your notes, and I will see you on Monday.